Okay, so I think I will get started. So yeah, in today's class, I want to first talk about this bootstrap. Okay, so we discussed like the logic and an example of the bootstrap last class. So today I want to see how we can implement this bootstrap in R. Okay, so we'll use the textbook example. So here's an example we use. So let me write. So this is the example we use. So this is a set seed. So this is like the I'm sorry, the random number generator we will use, and this is exponential. Yeah. So this whole thing would give us xt equal to mu plus phi xt minus 1 minus mu plus wt, where wt follows a Laplace distribution. Okay, so just help you to recall like what's the example we see last class. So in last class, we generate a AR1 process, okay? And instead of assuming the error term follows a white noise, not white noise, follows a standard normal distribution, we assume it follows a Laplace distribution. Okay, so we do this because we will later show that if we use a large sample series of the coefficients or the estimators, it's not correct. Okay. All right, so that's what we do. And here we set mu equal to 50. So you can see here we set mu equal to 50. Okay. And the phi, which is the AR coefficient, equal to 0.95. Okay. AR coefficient equal to 0.95, and we'll generate 100 data points. Okay, and here's the innovation. So in this command, the innovation is the DE. The innovation is basically the WT, and this DE would is generated in this way, like E times the sine of U, where E is like follows this exponential, and U follows this uniform distribution. Okay, but anyway, so this would give us this AR1 process. So this command would give us the AR1 process where WT follows a Laplace distribution. All right, so now we have like 100 data observations. So I can show you what his dx looks like. Okay, so this is dx. You can also plot dx. Okay, and this is like the plot. All right, so then we will use this 100 data points to fit a AR1 model. Okay. All right, and we look at the coefficients. Okay, so after fitting a AR1 model, after fitting an AR1 model using this 100 data, we find mu equal to 55.85, so which is this first coefficient. Okay, so this is just the mean of the fit. Okay, and the AR coefficient now is equal to 0.96. Okay, so it's like the fit AR coefficient. And we also record like the variance of this error term. Okay. So the sigma is equal to 8, or I think the sigma square. Yes, the sigma square is equal to 8. Okay, so all these numbers are very close to the true data generating process. Okay. Yeah, so remember the mu we put for the data generating process is 50. The phi, which is AR coefficient, is 0.95. And what we got is for the mu is 45, and for the AR coefficient is 0.96. Okay, so very close to. Sorry, this is 7.88. So this is so those numbers are very close to our data generating process. And also, I discussed I might not discuss, or I may discuss. So if you do a Laplace distribution, and if you like put those like numbers for the parameters of your Laplace distribution, the sigma square you get gonna be 8. And what we got here is 7.88. So which again is very close to the true data generating process. Okay, so everything looks good. Okay, so that's our step number 1. So we estimate the phi from a fake data set. Okay, and we got the correct answer, which is not surprising. Okay, and now the second step is that we try to find the theoretical confidence interval of phi. Okay, so what is the theoretical confidence interval of phi? So the theoretical confidence interval is basically phi plus minus 1.96, where 1.96 is like the z value. Okay, at 95% confidence interval, then times the standard deviation. Okay, so we learned this like at the very beginning of our class, so we know like the large sample series of the AR coefficient. Okay, so here we just use that formula to find the theoretical coefficient of phi. Okay, and this is what we will get. Okay, so that's the coefficient we get. So the theoretical coefficient of phi is is this number. So you can see what I got here is that basically phi minus the Q norm 1 minus alpha. So Q norm is like the quantile of the normal distribution. So it's going to be like 1.96 and times the standard error. The standard error is calculated in this way. So you can check the notes like for the detail of the standard error. Okay, and the upper bound is phi just plus 1.96 times the standard error. And this is what we got. That's the theoretical coefficients of phi. Okay. And remember, like our goal or our idea is that we would show that the theoretical confidence interval of phi is not correct. Why this is the case? Because the couple of reasons we discussed last class. First is that the data set we have is pretty small, right? We only have 100 data observations, but for the large sample theory to hold, we usually need like more than 100 observations. That's reason number 1. And reason number 2 is that the error term now, instead of following a standard normal distribution, it now follows a Laplace distribution. And number 3 reason is that the coefficient, the AR coefficient we have here is pretty large. It's like about 9.95. So it's very close to the boundary 1. So once it goes to 1, then that means it's not a stationary process, right? So here 0.95 is pretty close to 1. So that means this process is not that stationary. Okay, so all this reason will later show that the theoretical confidence interval we get is not correct. Okay, so our next step, step number 3, is to find the correct confidence interval of phi. Okay, and how to do that? So one way, which I mean we didn't discuss, is that you will use a theory to find the confidence interval of phi. But here, since the WT, the error term, does not follow a normal distribution, so you need to reconstruct the theoretical confidence interval of it. Okay, and another relative easy way is to use bootstrap. Okay, and how we use the bootstrap? So the idea is that the idea of the bootstrap is that we will generate. So here you can see this is like a for loop. Okay, so for each time we will generate, you can see we will generate like 100 data points. Okay, so X now is like this 100 data points, and 100 data points follow from the true data generating process, which is like the mu is 50 and the AR coefficient is 0.95. Okay, so for every time we will generate 100 data from the true data generating process. Okay, and then we will use that 100 data to fit an AR model. Okay, and then we will take the coefficients of like each, we will take the AR coefficient of that fit. Okay, so this is what we do here. So we generate, each time we generate 100 data points, and we use that 100 data points, which is this X, to fit an AR model on that. then we will take out of this AR coefficient. Okay, and we will do this like for a large number of times, and here we just do it like 1,000 times. Okay, so after doing 1,000 times, so that means we will have 1,000 AR coefficients, right? So that means we will have a distribution of the AR coefficient. Okay, so let me show you this. So if we run this, and you can see this is the density of the AR coefficient after 1,000 repetitions. Okay, so you can see here we have n is equal to 1,000, and this is like the density. Okay, you can see like most of the data points are very close here, like approximately 0.94, 0.93. Okay. All right, and if then we find the 2.5 and the 97.5 like quantile of this density distribution, then you will find then that would give you the 95% confidence interval of the true phi. Okay, so we find the correct confidence interval of phi now is 0.7666.791. Okay, so that's the correct coefficient. And to find the correct coefficient, we just use the bootstrap. We bootstrap from the true data generating process. Here we do it 1,000 times. And for each time we find its AR coefficient, then we will have like 1,000 AR coefficients, which give us like this density distribution. Then we just use the 2.5 quantile and 97.5 quantile of this density to find our correct confidence interval of phi. Okay. And now you can see this is what we got. This is a correct confidence interval of phi. It's 0.766 to 0.961. And surprisingly, you can see that the correct confidence interval of phi is very different from the theoretical confidence interval of phi. Okay, and I said that the overlap actually is not that large. Okay. All right. And what causes this? I discussed a couple of reasons causes. First, the data set we have is small. Second, the error term now follows a Laplace distribution. And number three is that the AR coefficient is relatively large, okay, very close to the non-stationary boundary point. Okay, so as you can see, the correct coefficient, the correct confidence interval of phi is different from the theoretical confidence interval of phi. Okay, so this is good, but so that means like in practice, we need to use this correct confidence interval of phi instead of using this theoretical confidence interval of phi. However, I mean, unfortunately, we actually do not know the true data generating process. We do not know the true phi, or we do not know the true mu. So we know nothing about it, okay? So that means how can we find the confidence interval? Right? So you can see that in order to get the correct confidence interval of phi, we need to know the true data generating process, right? So we generate like 100 data points from the true data generating process, and we do that 1,000 times, okay? However, if we do not know what is 50, what is mu, what is the AR coefficient, or what is like the distribution of the error term, how can we do that? There's no way that we can do this step. Okay, there's no way that we can find the correct confidence interval of phi, right? Then the question comes, how can we find the confidence interval? Because we know like the so-called theoretical confidence interval of phi is actually not correct, right? Then how can we find the confidence interval? The answer is that we will use bootstrap again, okay? So this time, how we use the bootstrap? So this step, we use bootstrap in this way. So we think that for now, just think that we know nothing about the true data generating process. All we know is this 100 data points from the step number one. Okay, so in a data set, you will have like, say, like 100 data observations, but you do not know what, you do not know what is the underlying data generating process of that 100 data points. You only observe 100 data points. Okay, so that's like the real empirical question you will face, or the real empirical data you will face. Okay, so right now you only have this 100 data points from the beginning. Okay, at the beginning of like this example. Okay. All right, so the idea here to use Bootstrap is that we will use, okay, so we will use the AR coefficient, which is the fit. So we will use the fit of that 100, I'm sorry, we'll use the AR coefficient, which is the fit of that 100 data points as our like as our fee for like data generating. Okay, so I mean, let me re-say this again. So we will use, so from that 100 data points, we will get a AR estimate, and we will get like the mu estimate. And we will use that AR estimate, and we will use that mu estimate as our fee coefficient and as our mu coefficient, okay, for our later data generating process. Okay, so if you know the true data generating process, you will use the true AR coefficient and use the true mu for your data generating, for your Bootstrap. However, since here we do not know the true mu, we do not know the true AR coefficient, so we will just use the estimated AR coefficient and the estimated mu coefficient to replace our true AR coefficient and the true mu coefficient. So that's the idea. Okay. All right. So all this like R codes are just doing what I just said. So we will use the estimated AR coefficient and the estimated mu coefficient as our data generating process coefficient. Okay, and we will generate data based on that. Okay, so we will generate data, say like we will generate like 100 data points, and we will do this Bootstrap number of Bootstrap here, which is choose 500. Okay, so for each step, we generate 100 data points, but instead of using the true mu and the true AR coefficient, we use the estimated AR coefficient and the estimated mu coefficient. Okay, and once we generate that 100 data points, we will estimate its AR coefficient again. Okay, and then we will do this like for a large number of times, and in this example, we'll just do it 500 times. Okay, so after this 500 times repetitions, you will have like 500 ARs. Okay, and that AR will also give you a distribution of the AR coefficients. Okay, so let me run this and show you the results. Okay, so it will take some time. Okay. All right, so now here this phi star YW now is a collection, a 500 collection of the AR coefficients. Okay, so I can plot the density of this. All right, so this is a density plot of the 500 AR coefficients. Okay, and surprisingly or not surprisingly, you can notice this density of the phi, okay, which is we estimate using the estimated phi, is actually very close to this true density of phi. Right? So this this density plot is the density of the true phi, while this density is the density of the estimated phi. And you can notice that they are actually very close. Okay. And if you use the estimated density to find the confidence interval of your phi, you would get this number. Okay. So the Bootstrap confidence interval of phi now is 0.781 to 0.967. Okay. The key point is that it is very close to the correct confidence interval and very different from the so-called theoretical confidence interval. Okay, so you can notice that this confidence interval is very close to the true confidence interval, and it's very, very different from the theoretical confidence interval. Okay, so you can see that the bootstrap actually help us a lot. So it helps us to find the true confidence interval from basically from any data generating process. You can do that. Okay, but I mean, in the R package, it usually just gives us this, the so-called theoretical confidence interval phi. Sometimes it is correct, but sometimes it is not correct. But this step, this bootstrap algorithms can always provide you the correct confidence interval. Okay. So any questions about this? Or I mean, the code might be a little bit hard if like this is your first time to see this. But I mean, do you have any questions about like the algorithms of the bootstrap? Okay, so if there are no question, I think I want to move to the next topic, which is another like extension of the ARMA model, which is called the threshold autoregressive model. Okay, so let me switch to the whiteboard and talk about that model. Okay. All right, so today I want to talk the threshold autoregressive model. So just to recall, like one key assumption of the ARMA or also the SRAMA model is that it is gonna need to be stationary. Okay. So one actually the key assumption. So without this assumption, like all your fate basically is not correct, right? So we need to do like those transformations. We need to do those like seasonality transformations in order to make our model stationary first. Then we can do all the model fits. Okay. So one key assumption of the ARMA model, or definitely the SRAMA model, is stationary. Okay. So one way to say this is that the distribution of x1 to xn, okay, should be the same as the distribution of xn to x1. Right, so this is basically the the variance is the same, and the autocovariance only depends on the lag. It does not depend on time. Okay, so we will see that the distribution of our x1 to xn gonna be the same as the distribution of xn to x1. Okay. But unfortunately, this might not be the case. And people realize that in many like economic applications, it is usually that before some threshold, xt is stationary, and after some threshold, xt is stationary. Okay, but the stationary, like in those two parts, are different. Okay, so economists Okay. And after the whole process is not stationary. Okay. And the threshold, what is the threshold, or what could be the threshold, or what could be a potential candidate of the threshold? So the threshold can be a policy change, or it can be introduction of a new product. Etc. So very easy to understand, I think. So for example, suppose like there's a minimum wage increase, then what is like the unemployment rate? Okay, so before the minimum wage increase, like the unemployment is maybe follow some distribution, follow some process, and after the minimum wage change, then there's maybe follows another process. And also like the introduction of a new product would also maybe have that effect. Yeah, so I remember like, I think one IO paper studies like, yeah, cannot remember the details, but it just discussed like, what if I introduce a brand, or I mean a new cereal, then what would happen to the cereal market? Okay, yeah, and I think that paper, yeah, I cannot remember the detail. Okay, anyway, yeah, but you can think that the thresholds like actually happen a lot. Okay, so based on this, we can have a somewhat called like the threshold ARMA model. Okay, so now let me introduce a model. This is called a SETAR. Okay, and the model follows this. So XT is equal to 301 301 plus I1 XT minus I plus WT1. Okay, so if XT minus D is less than R. Okay, and it is equal to 302 to VI2 XT minus I WT2 if XT minus D is larger than R. Okay, so let me explain this model a little bit more. So first, you can notice that this is basically like a two regime model, right? So if XT minus D is smaller than R, it follows this AR process, okay? And on the other hand, if XT minus D is larger than R, then it follows this AR process. All right. WT1 and WT2 here are just white noise. And the difference is that the AR coefficient in each regime is different. Okay, so we use like 1, 2 to distinguish each of the coefficients, the coefficient in each regime. Okay, yeah, and a couple of questions that you might ask here. So yeah, and I think I need to explain one thing. So here the regime is depend on like this XT minus D, and it is basically like a one observation in the data. So that's why we call it like it's the self-exciting threshold AR. Okay, so a couple of things that's or a couple of remarks, I think that might answer some of your potential questions. Okay, so remark number one. Okay, the threshold here depends on xt minus d. Okay, so this, yeah, to me, it's like a little bit arbitrary. So what is xt minus d? Or to be more specific, what is d? How can we choose d? Okay, so this can actually be generalized. Okay, so I think this generalization might make more sense. So this can be generalized that the regime depends on a collection of past values. Okay, so for example, f xt minus 1, xt minus 2, less than r. Okay, so this looks better than this xt minus d is smaller than r or greater than r. So we say that f, like a function of previous values would decide whether we are in regime 1 or we are in regime 2. Okay. And actually, the threshold can actually depend on some other variables. Okay, so for example, so let's see this example. So for example, so suppose I want to use a AR2 model to study the interest rate. Okay. However, I think like the evolution of the interest rates actually depends not only on its past values, but it also might depend on whether the economy is in the recession or not in the recession. Okay, so you would say that I have to use like regime number 1 if economy is in recession and if economy is not in recession. Yeah, so here you can see the threshold variable is not interest rate itself, but it's some other measurement or some other variables. Okay, and this is actually like the I like do some like analysis on this when I was in the second year of my PhD. So I do this. I do like I run like this like two regime. So I instead of running like this AR model, I run like a vector AR model. So it's like the VAR model to study like the effect of the how we can model the interest rates and the employment rates. Okay, and the regime I choose is that when the economy is in recession and the economy is not in recession. Okay, so that's yeah. So I also like use this like regime model in my previous studies. Okay, all right. So we know that the threshold can depend on itself or it can depend on some other variables. Yeah, but you might still have the question. For example, so how you choose this R, okay, or how you choose this F function, or how many like XTs I want to include in the threshold, okay? Or you might also wondering why you want to study the economy in recession or economy not in recession. Why don't you choose some like other measurements of the economy to construct this two regime model? Okay, so the question is that basically like choosing the threshold, basically like xt minus d, this f function, this r, or the economy. In recession. Okay, so to choose like both, like all those stuff are like the threshold related variables. So those would depend on a lot of things. So it's actually not easy. So it depends on like your preliminary data analysis. It also depends on your research design. Also depends on your model fit, and etc. So it really depends on a lot of things. Okay, so yeah, so in the it just depends on a lot of things. And I think to start with, you might start with your research design. So for example, for example, you might start with like the economy is in recession and the economy is not in recession as your starting point, because that's very easy to tell. That would affect the interest rate. And after that, you fit the model. And if you think that the model is not good fit, so I mean, after a lot of model selection, you still find like your model is not in good fit. Okay, then you might think, okay, does that exist some other variables that would also affect these two regimes? Okay, so for example, do I want to have more regimes, or I don't know, or do you want to include some other measurements in the model? Okay, yeah, so that really depends on a lot. Like choosing the threshold is not that easy. Okay, so after you choose the threshold, you can imagine that fitting such AR model is actually very straightforward. So we know how to do that. Okay. All right, so that's remark number one. And let's talk a little bit more. So as we said, we can generalize two regimes to multiple regimes. Okay, and actually the more the regimes, the more nonlinear patterns it can capture. So the regime regression is one way to think about this regime regression is just to think of it as a nonlinear regression. You can think each of the regime as I don't know, like some the dummy variables or discrete random variables, and that would cause like your slope and the intercept in each regime to be different. Okay, and you can think that the more regime you have, like the more curvatures your model can capture. All right. But the benefit of like fitting this regime model is basically the threshold AR model is actually easier to specify, to estimate, and to interpret, as compared to many nonlinear models. So in the nonlinear models, so for example, you can say that xt is equal to phi xt minus 1 plus phi 2 xt minus 1 square plus wt. Okay. Yeah, in this case, it's a little bit hard to understand like what is xt minus 1 square in the model. Or maybe xt minus 1 square is not that bad, but how about if I have like xt minus 1 to the cubic? Okay, so the quadratic might be a little bit easier to understand, but why I want to have a cubic term? Okay, but instead of this, you can somewhat like construct a threshold AR model to represent this. And in the threshold regression model, AR model, we know that it's actually very easy to understand, right? In regime 1, we have like this process, and in regime 2, we have this process, and maybe in regime 3, we have another process. So it's relatively easy to understand and to estimate for this regime threshold regression model. Okay. All right, so that's the theories, or not a theory. So that's a setup of the threshold regression model. So any questions on that? Okay, so now I think I want to go to R and work you with an example. Okay. All right, so this example is the example of the flu. Okay, so we first generate a variable called d flu, which is the difference of the flu. Okay, the first order difference of the flu. And we plot d flu versus d flu lag 1. So let me show you the plots. Okay, so the y-axis is the d flu at time t. Okay, and the x-axis is the difference of the flu of lag t minus 1. Okay, so why we do this? Because we want to use this difference of the flu t minus 1 as our threshold variable. Okay, so that's just the reason why we want to plot that. And we want to see if we plot like this graph, can we see some threshold? Okay, so, and we can easily see yes, looks like there's some threshold at d flu t minus 1 equal to 0.05. Okay, so you can see that when the difference of the flu t minus 1 is less than 0.05, then there's a increasing pattern, right? So you can check this red line. And if the difference of the flu is larger than 0.05, then you can see there is a decreasing pattern, or there's a decreasing fit. Okay. So this would imply us that the threshold would be 0.05. Okay, but 0.05 is just that we just look at it by this I mean, by this graph, I mean, like in your fit or in your applications, you might also want to try like 0.04 or 0.06 or maybe even 0.03 at your threshold and do a bunch of like model fitting and select the best model. Okay, yeah, but just for the illustration purpose, we just use the threshold as 0.05. Okay, so. Okay, all right, yeah, and I again follow the textbook, and in this example, we will fit a AR4 model to the difference of the flu. Okay, but again, as I said, in your application, you also maybe want to try AR3 or AR5 or even AR6, okay, and do like a lot of the model selection process. Okay, so let's construct the data. So the data is now called Z. Okay, so Z is like the TS intersect. It will just combine the difference of the flu, the difference flu -1, difference flu -2, difference flu -3, and difference flu -4. Okay. All right. Then here's the key part. Okay, so since we want to fit a two-regime model, so basically we will need to separate the data into two groups. One group is that the difference of the flu T-1 is larger than 0.5, and the other group is the difference of the flu T-1 is smaller than 0.05. Okay, so that's how we do it. So we will use two indicator variables to do that. The first is called like the indicator 1. Okay, so indicator 1 is like an if-else statement. So it says that if your Z2, so the second column of Z, where the second column of Z is just our threshold variable, which is difference flu -1. So if this variable is less than the threshold, then we will give it 1. Otherwise, we will give it NA. Okay, so you can let me run this. So that's the indicator variable 1. Okay, so in let's say like June 1968, it is 1 because let me pull out the raw data, Z2. Okay, so in day 2, so you can see that June 1968, it is negative 0.02. So it is smaller than the threshold, so we will give it 1. Okay. However, in December 1968, let's see what is December 1968. In December 1968, the number we have is 0.056, so which is definitely larger than 0.05. So we will give it NA. Okay. So the indicator 1 just gives us one regime, and we need another indicator variable to have our second regime. Okay. So that's our indicator number 2. So in indicator number 2, we say that if our threshold variable is smaller than the threshold, we give it an NA, and on the other hand, we'll just give it 1. Okay, so you can check this is our indicator number 2, okay, which is just the opposite of the indicator number 1. All right, so now we have two indicators. All right. So then the next step is that we will use these two indicators to basically to reconstruct our data. Okay, so we have the first group of data called X1. Okay, so X1 now is equal to the first column of Z, which is the difference flu, which is our dependent variable, which is our Y variable, right? And we will times Z1. I'm sorry, we will times it with indicator 1. Okay, so that means whenever the like indicator 1, whenever it is NA, our new dependent variable, for example, here, gonna be NA. Okay, and when it is not NA, it is just like its original number. Okay, so for example, in June 1968, it's still like 0.004, right? You can say that in Y. Let's see. Yeah, I think I put wrong data. Yeah, so that's Z1, and in June 1968, it's 0.004, and times 1 is going to be still equal to 0.004. Okay, and however, if our indicator tells us it is NA, then let me see. For December like 1968, it's going to be NA. Okay, so we will construct a new difference of flu. Okay. Similarly, we will construct the different flu in the other regime, and let's call it X2. Okay, so now X2 is Z1 times the indicator 2. Okay, so we will create new data for the two regimes. All right. Okay, then the next step is basically to just run this regression. Okay, so we first run the first regime regression. So we run fit so fit one is we run x1 over z. The second column for, we use the 4 legs to predict the difference of fluid, and this is our regression results. Okay, so this is basically a AR4 model. And you can notice that everything except the intercept looks pretty good. But the intercept itself is just pretty much equal to 0, so ignore it. Okay, so everything looks good. Okay, so in regime 1, this AR4 model looks pretty good. Okay, and how about in regime 2? How about this AR4 model? And we notice that seems like the AR3 coefficients is a little bit off. So it's just a little bit like marginally significant, but everything else looks pretty good. Okay, so overall, it looks like the AR4 fits like it's a good fit for our y variable, for our dependent variable. Okay, so so the regression results show the 2 regime AR4 is a good fit. Okay, but I mean, this is just for the illustration. Like the main purpose of this example is to tell you how to fit a regime regression. But I mean, like in real applications, you would change like maybe this AR4 to, I don't know, AR5, AR3. You can run the ACF and the PACF plot to do that. Okay, and you definitely also want to change your threshold. So it looks like this threshold looks not bad, but you might also want to check how about like 0.04 or how about 0.06. Okay, and I mean, even if when you want to do it like more ambitious, you can try some other combinations of like the difference of the fluid to construct other thresholds. Okay, so you can maybe combine difference like the d flu t minus 1 with d flu t minus 2 and plot that against your d flu t and see like what is the threshold. Okay, and you refit that model and compare it with your principal model and decide which is the best model. Okay, but I mean, for the illustration purpose here, we just fit an AR4 model to the data, and it looks like it looks pretty good. Okay, all right, and then what we do is to evaluate this model, we do some predictions. Okay, so here's a prediction. So this red dot are the true data, and these black lines are the fitted data. Okay, so or the prediction data. So you can see that the prediction, which is this black line, fits the true data pretty good. Right, especially like in this central area, in the center area, in this area, like in the difflu across like around 0, it fits good, right? It actually captures, I think, all the up and down here. However, we can notice that for those like large data points, you can see right here, especially here, and also like these points, the model fit seems it's not that good. Okay, so it seems like this AR4 model cannot capture those maybe outliers or something like that, or this like large points or very small points. Okay, so that may suggest that this 2 regime AR4 model might not be a very good model. So as I said, you can increase the order of the AR model, or you can change the threshold, or even you can include more thresholds, include more regimes. Okay, so the fit is overall good, but it misses some large points. So we might want to try some other models. Okay. So any questions about this example? Okay, so I think if there's no questions, I think that's the threshold regression I want to talk. And I think I want to use the rest of the time to do our final quiz. Okay. Okay, let's say another 30 seconds. I think I have all your answers. And poll, share results. Yeah, so all of you got it correct. So sure, if we have like non-constant conditional variance, we will just use the Garch model or the Arch model. The Garch is just a extension of the Arch and captures more features. Okay, so very good. Let's do the second question. have another 30 seconds. Okay. I think it's time. All right, so yeah, the answer is gonna be C. So both A and B. So yeah, it's a little bit tricky. So yeah, so if the residual plots are not good, so I say it's like autocorrelated. So that might tell you that you want to like the error term has some, I don't know, like the error term has some serial correlations, so you'll fit in as a Riemann. But if it's like heteroscedasticity, then you might think that you want to include more X variables in that. So for example, if you realize that your residuals, I don't know, have like a quadratic pattern, then definitely you need a quadratic term. If like a cubic pattern, definitely a cubic term in that. Okay, yeah. So both A and B, and I mean, in your project, if you find such problems, and of course in your future research, if you realize such problems, like having more X variables and give some structures to the error terms are usually what we use. Okay. All right, so that's the quiz, and I think I have maybe 10 more minutes left, and I just want to use that 10 more minutes to just do a very quick summarize of what we learned this semester. Okay, so let me switch. Okay, so a quick summary of what we learned this semester. Actually, I think we actually learned a lot this semester, and this is my first time teaching this class. Yeah, so I'm pretty good, happy with the results. So we start with like the series of time series basic. Okay. So we start like with the stationary. We know how to do the ACF. We know how to do the CCF. We know how to do the AIC, BIC, and we know how to do the transformations. Okay. So we learn all those definitions. We learn how to calculate it. We know how to implement those in Rs. And also, more importantly, we know why we need all those stuffs. Okay. Then we use all those stuff to build our S-Riemann model. Okay. So we start with the exploratory data analysis. Okay. Then after the exploratory data analysis, we do our model identification. Then estimate our model. Then we check our model diagnostics. And we do model selection. Okay. And finally, we use that model for forecasting. Okay. So very good. And again, we know how we can do all those stuff in R. So we know how we can fit an S-Riemann model. We know how to do all those steps in R. Yeah, and the last step is that we took some extensions of S-Riemann. So for example, we say that what if, how about like we include some XTs in S-Riemann? So how about we include some regressors in S-Riemann? We talk a little bit about the Arch and Gotch. Those models are very useful for the financial data for the asset pricing. And we also, in today's class, we talk a little bit about like the threshold AR model. And this would be very useful if like your data sets contains some policy change or some maybe like the introduction of a new product. Okay, yeah, so that's pretty much what we learned this semester, and I think we did pretty good. And I think that's like from all the exams or the homeworks and also your project, I think you guys can pretty much get all those stuff. So I think I'm very happy, and of course I look forward to reading your final project. And if you have like any questions about your final project, or I mean anything about like econometrics time series, just feel free to reach out. And that's it for this semester. So thank you very
Professor,
much.
thank you so much. It's been an honor. This is my last undergrad class, learned a lot, and I love you and thank you so much.
Yeah, thank you. All right, so if you have questions, I have office hours tomorrow. So feel free to come if you have questions about your project. And I'm also available right now. So if you want to talk about your project. Okay.
Dr. Zhang, I actually have a question.
Yeah, I have questions. I would like to stick around just to ask some questions if that's okay.
Yeah, sure.
Okay. Somebody else I think also have questions, but they can go first.
Okay, mine's pretty simple. I just want to, this is Gabe, and I'm doing the cross correlations one. And I'm doing it like the homework 4, but I just can't get it to be like I've pretty much figured out the linear regression between the two of them, and then I fit a Surima to the error. I just don't know how to put all of that into one model. Like, I don't know how to write that so that like R will recognize it as a model that I can get AIC and BIC for.
I'm sorry, so you said that it's homework 4.
Yeah, I'm doing it like
Okay.
5.1.3. So like I've basically gone through and I've done the intersection. I found I did the linear regression between them, and I did the Surima fit on the residuals. So like I have that, I just need to put them into add them together basically. But I can't get R to read that.
I'm sorry, to R to can you tell me which specific? So 5.3.
5.13.
5.1. So 5.13, right?
Yeah, 5.13.
Okay, so which parts you have questions on?
Well, I guess I did B and C. So basically what I did is I did like a regression between 2 variables, right? And then I took the residual of that fit and then I fit a Surima to it, right? Or an ARIMA. I've done that, and now I need to basically add them together into delta ST equals beta naught plus beta 1, yada, 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 right? Into the full model. But I just don't know how to enter that into R so that I can get AIC, BIC residuals, ACF residuals, stuff like that.
Yeah, so the code, did you see the solution?
Yeah, I've been looking at the solution.
Right, so so part C, so did you see fit 2 equal to S ARIMA, then DS100, did you see that? It's the last but 3 line, 3 by last one.
Okay, yeah, I do see that.
Right, so that's how you put the S ARIMA together with the X regressors.
Oh, okay, awesome, thank you. And then you said you had office hours tomorrow?
Yes, I do.
At what time?
Yeah, you can come by 1:30 tomorrow. Yeah, does that work for you?
1:30, yeah, that works. I can meet you at 1:30.
Okay.
Thank you.
All right, so I'll see you tomorrow. Yeah.
Okay, so I'm just these are just some follow-up questions on what we did yesterday.
Yeah.
So we played around with the disaster variable idea, and it's worked really, really well so far.
Okay.
We were wondering if it was possible to switch that over to if we switched it over to the regular data where it's not logged. What would we need to change the?
Go ahead.
Oh, yeah. If we didn't use the log transformation, and we went with using the original values, would we need to change the values from 0, 1, 2, 3, 4 to higher numbers to make it have more of an effect on the
exactly. So so you have so if you change to the original data, to the raw data, then it's gonna be very large, right? So you perhaps want to have like more intervals, right? So like, for example, maybe from 100 to 200, it's 0, 200 to 300 is 1, 300 to 400, it's 3 or something like that. So you need to have like more intervals. Is that
More. Okay.
what you're asking for?
I mean, more that it should the value that the discrete variable takes on. Originally in the log transformation, it's 1, 2, 3, 4 because the log values are very low. Should it be because like the unemployment claims are in the thousands and for continued sometimes in the 100,000s? Should it be like, should the discrete variable take on values like 1,000, 2,000, 4,000, or like 100, 400, 200 instead of just 1, 2, 3, 4?
If I understand correctly, just be 1, 2, 3, and 4. Don't do. You can do 100, 200, 300, 400, but I don't think that makes. I mean, that's just the same. It's just like a rescaling. It won't affect your answer. Yeah.
Okay.
Yeah.
And I was having trouble with like the X regulator for forecasting in ARIMA because it says I have to include a new X reg.
Correct.
I don't know exactly. Like, I know, does that mean I have to forecast the values for the X reg I was using before?
Yeah. So you need to like some X, which I think like in your case is like COVID, right? But you actually do not have like those COVID, right? After your data sets, they are just not happening. They are just not. They're just not. You can just not observe it. So I provide some. I mean, in my notes, I provide some solutions to that, which might not be great, but you can try. So first is that you just think that, yeah, in your case, it might work because you like group make the intervals on the COVID cases. So I think maybe after say like May this year, May 2021, the COVID case is going to be low. So in that sense, that means your X gonna be 0 or 1 because the COVID case might be very low, right? I think that in your case, it's just, you can just say it's 0 because it's very small. There won't be many COVID cases after May, I think, right? Because of the vaccine. Yeah, that's one way, and which I think might work for you. And another way is that you can just first fit a SARIMA on the COVID itself, then use that model to predict the future COVID. You understand what I mean? So you use like the COVID from 2020 to like from like January 2020 to April 2021, right? Then you use that period of data, then you fit an SARIMA to that data, and you use that model to predict, like say, like the May 2021 COVID, June 2021 COVID. So that's another way. Yeah, so that's 2 ways, but I think the first way might just work for you. The second way is also work for you, but I guess the result's gonna be the same as the first approach, I think. Yeah.
How would we do that for the disaster variable?
Yeah, so that for the design. Right, but yeah, like the disaster variable we discussed is like there are a couple of disasters like in your time period, right? It has like the financial crisis, has this like COVID, it has like the hurricane, right? So all those stuff. So yeah, you just think that maybe for a short period of time, there won't be any disasters. So the disaster can be 0. So the only disaster we have right now is the COVID, and you think that the COVID case is gonna be low in the next couple of months. So you just have 0 or 1 for the disaster variable. Yeah.
Okay. Awesome.
Okay.
That clears it up.
Okay, great. Okay.
Hey, Professor.
Yeah.
It's this is Brad. Our group had a question about the convergence of it's SARS and what exactly, how do you explain what we were doing? When we were doing the round?
Yeah, we were testing the causality and
invertibility. Yeah, that's it.
Yeah.
So
okay.
So when we had like we did max lags like 50, it didn't show convergence, but when we increased it more, we found that it converged after like 700. Does that,
Yeah.
if it converges at all, is that still considered converging?
Correct. Yeah. So we just
It doesn't
want,
matter
like,
how
the-
many lags.
Yeah, we just want it to be converged at a finite time of lags. That's what we want. 700 is definitely finite, so we are good.
Okay,
Yes.
that's the main question we had. Do y'all, Morgan, Saracen, do y'all know if we had any other question?
I think that was all we had.
Yeah, I'm looking at my notes. I just was looking at a second ago. I think that's the only thing that we jotted down from when we met.
Okay.
But so y'all are sure that's all for now, at least?
Yeah.
All right, thanks, Professor.
Okay. Great.
I have one more question, just about how detailed do the papers that we're writing have to be? And do we have to do like anything on like Converge?
Yeah. So yeah, though that would be ideal. So yeah, that's what I want to see. But yeah, so yeah, that's what I want to see. But I mean, in your case, like doing the convergence might be a little bit tricky, and yeah, I don't think I spend much time on that. So yeah, in your case, because you have a X regressors, like the disaster regressors in that, so doing the convergence